Assalamu alaikum students, today over topic Pharmaceutics-l Chapter 5.
Chapter 5 Surface Tension. The boundary between two phases is generally described as an interface. When one of the phases is a gas or a vapor and the other a liquid or solid, the term surface is commonly used. Surface tension is defined as the force acting over the surface of the liquid per unit length of the surface. Force per unit area, F/A, on surface of liquid. Its unit is Newton per meter, N/m². Explanation. The molecule inside the liquid interacts equally with other molecule from all sides, whereas the molecule at the surface is affected only by the molecule below it. The molecules exposed to air behave differently. Surface molecules are compressed more tightly together, forming a sort of skin on the surface, with less distance between them compared to the molecules below. The molecules on the surface of a liquid are attracted only sideways and towards the interior, so surface molecules are being pulled inward the liquid. Liquid surface is therefore under tension and surface area of the surface molecules is reduced. Water in particular has a very high surface tension. This explains the characteristic rounded shape that liquids form when dropping through the air. The molecules are all being pulled toward the center. Factors affecting surface tension. Intermolecular forces. Surface tension increases with the increase in intermolecular forces and decreases with the decrease in intermolecular forces. Hydrogen bonding. Surface tension increases with the increase in hydrogen bonding and decreases with the decrease in hydrogen bonding. Temperature. Surface tension decreases with the increase in temperature and increases with the decrease in temperature. Applications. Emulsifying agents reduce the surface tension of oil and water phase, which results in stabilization of emulsion. Bile salts reduce the surface tension of fats in duodenum, which results in solubilization of lipids, which help in the digestion of lipids. Viscosity. Viscosity can be described as it is the internal resistance of the molecules of any liquid to flow called viscosity. Viscosity is the fundamental tool to check the internal friction of any liquid, like water is thin so it has lower viscosity, and on the other hand honey is thick so it has higher viscosity. Viscometers. These are the specialized equipment and apparatus used for the determination of viscosity of different liquids. Types of viscometers. There are various types of viscometers. The most famous are Ostwald viscometer or U-tube viscometer, rotational viscometer, falling ball viscometer. Factors affecting the viscosity. Temperature. Viscosity decreases with the increases in temperature. Size of the molecule. Viscosity increases with the increases in size of the molecule. Molecular shape. More irregular the liquid's molecular shape, greater would be the viscosity of the liquid. More regular shape of liquid's molecule, lesser would be the viscosity. Adhesive forces. Stronger the adhesive forces, greater would be the viscosity of the liquid. Cohesive forces. Stronger the cohesive forces, lesser would be the viscosity of the liquid. Application of viscosity measurement. Viscosity determination is the fundamental quality control test for syrups, suspension thickness, and consistency. Viscosity is also given us the indication regarding quality and purity of liquid raw material. Viscosity tells us about the thickness of liquid substances. Viscosity determination is also a key quality control test for oil-based injections and suspension. Viscosity enhancers, e.g. methylcellulose, hydroxyethylcellulose, are used in ophthalmic solutions to increase their viscosity. This enables the formulation to remain in the eye longer and gives more time for the drug to exert its therapeutic activity or undergo absorption. Ionization. Atom. Atom is derived from Greek word means undividable. It is the smallest particle of an element, which cannot be further divided. It consists of central nucleus containing protons and neutrons and outer shells in which electrons are revolving. Protons carry positive charge, neutrons are neutral particles having no change, and electrons carry negative charge on them. These are called fundamental particles of atoms. ION. Any charged particle is called ion. It may be positive, plus, or may be cation, plus. When an atom loses an electron from the outermost shell, cation, positively charged atom, is produced. Anion. When an atom gains an electron from the other atom, anion, negative charge atom, is produced. Ionization. Process by which electrically neutral atoms or molecules by the removal or addition of electrons. In this process, an atom acquires net positive charge on it. Ionization energy. Amount of energy required to remove an electron from an atom. Ionization experiment. In 1897, J. Thomson conducted the famous discharge tube experiment by passing electricity at high voltage a gas at very low pressure. The pressure of air in the discharge tube is reduced to 0.001 millimeters of mercury, and a high voltage is applied to the electrodes. When electric current passes through the discharge tube, ion of given gas produce. Some ion carry negative charge, and some are neutral, creating a condition of ionization. Applications. Many drugs are either weak organic acids, e.g. acetylsalicylic acid, aspirin, or weak organic bases, e.g. procaine, or their salts. The degree of ionization of a drug has an important effect on its absorption, distribution, and elimination. So ionization is an important factor which is considered during the manufacturing process of medicines. Ionization radiations are used in medicines and medical radiography to make image inside the body. In biology and agriculture, radiation is used to induce mutation to produce new or improved species. Radiation are used in sterilization of tools and equipment used in surgery. pH. pH involves taking negative log of hydrogen ions concentration. pH equals log H plus. This hydrogen ion concentration is usually expressed in moles per liter. Calculation of pH. Following formula can be used to determine the value of pH of different solution. For acid, pH equals log H plus. For base, it is the negative log of hydroxyl ion, OH, concentration. Po equals log OH dash, whereas pH plus Po equals 14. Explanation. pH of H2O is 7, and it is considered to be neutral. If pH falls down from 7, then the compound will be called acid. If the pH rises from 7, then the compound is called basic. Increased acidity, neutral, increased basicity. 1714. 10 to 7. Determination of pH. pH of a solution is measured by following methods. By using pH paper. By using pH meter. By using indicators. pH indicators are organic substances which have tendency to change their color with change of pH of the solution in which they are present. The aim to use pH indicators are to determine the type of compound, to determine the pH of different sample, to verify the presence of any chemical substance. Types of pH indicators. There are 3 fundamental types of indicators. Acid-base indicators 2. Redox indicators 2. Precipitation indicators acid-base indicators. There are the indicator that change their color as we change the pH of the solution. Example, methyl orange, phenolphthalein. 2. Redox indicator. These are the compounds that changing their colors during oxidation and reduction reaction, e.g. KMNO4. 3. Precipitation indicators. Those indicators that change their color during precipitation reaction are called precipitation indicators, e.g. K2CrO4, potassium chromium oxide. pH meter. It is an electronic instrument used for measuring the pH of a liquid or semi-solid. A typical pH meter consists of a glass electrode connected to an electronic meter that measures and displays the pH reading. Applications. pH measurements are important in medicine, biology, food science, and many other applications. Enzymes work at specific pH, so their preparations must be maintained at that pH. Blood has a specific pH of 7.3 to 7.4. pH indicators are used in titrations in analytical chemistry and biology to determine the pH of different substances. A titration is a technique in which a solution of known concentration is used to determine the concentration of an unknown solution. Buffer. Buffer is the compound or mixture of compounds that resist to changing pH of any solution on slight addition of acidic or basic solution or compound. Useful buffer mixtures. S.NO. Buffer mixtures. pH range. 1. HCl, sodium citrate. 1______5. 2. Sodium hydroxide and borax. 9.2_____11. 3. Citric acid/sodium citrate. 2.5_____5.6. 4. H2CO3/NaHCO3. Theory of buffers. Addition of acid. HCl is strong acid and it will change H plus concentration when added to a solution but buffer system. H2CO3/NaHCO3 tends to maintain the pH of solution and following reaction takes place. HCl plus NaHCO3 H2CO3 plus NaCl. NaOH plus H2CO3 NaHCO3 plus H2O. If we add H plus ions to the above-mentioned reaction, the reaction will shift to the left side H3O plus H plus. If we add OH ions to the reaction will shift to right side. Applications. Buffers are most widely used in biological industry to preserve the pH of biological compounds and fluids. In injection manufacturing, buffer are used to maintain their pH. 3. Buffer are used in fermentation process. 4. Buffers are used to preserve and restore the action of enzymes. B. Buffer are used to maintain the pH of drugs. Isotonic solution, isotonicity. If a solution is placed behind a membrane that is permeable only to solvent molecules and not to solute molecules, semi-permeable membrane, osmosis occurs as the molecules of solvent passes through the membrane. If a solution-filled membrane is placed in a solution of a higher solute concentration than its own, the solvent can pass in any direction, passes into the more concentrated solution until equilibrium is established on both sides of the membrane. The pressure responsible to prevent osmosis is termed as osmotic pressure. Body fluids, including blood and tears, have an osmotic pressure equal to that of a 0.9% NaCl solution. Or it can be said that 0.9% NaCl solution is isotonic to body fluids. Isotonic solution can also be defined as if two solutions on comparison have same osmotic pressure and ions concentration are termed as isotonic solution. The solutions, which have less ions, and it have less osmotic pressure than its comparative solution. Or solutions with a lower osmotic pressure than body fluids or a 0.9% sodium chloride solution are commonly called hypotonic solutions. Those are the solution in which the conc of the ions and osmotic pressure is greater than its comparative solution. Or solutions having greater osmotic pressure than body fluids or a 0.9% sodium chloride solution are termed as hypertonic solutions. A hypotonic solution added to body S system will lose water, and this water will be absorbed by body tissues. It may induce hemolysis of red blood cells. A hypertonic solution added to body S system will have a tendency to draw water from body tissue. So it can cause shrinkage of body tissues and cause complications. Solutions for injection, for application to mucous membranes, and solutions for ophthalmic use must be made isotonic with tissue fluid to avoid pain and irritation. The most widely used isotonicity modifiers are dextrose and sodium chloride. Applications of isotonic solution in pharmacy. Isotonic solutions are used in physiological experiments and tissue culture. Isotonic solutions are used to balance the electrolytes. Isotonic solutions are used to maintain the physiological conditions. For medical purpose, isotonic solution, normal saline, is used to flush wounds. Normal saline is also used I.V. for patients who cannot take fluids orally. Saline is also used for nasal washes to relieve some of the symptoms of the common cold.
Chapter 5 End.